Let us see now how to determine the solution of our congruence modulo prime power. So here we consider fx to be a polynomial over the set of integers, which means that fx is a polynomial with the coefficients over the set of integers, and consider m to be greater than or equal to 2. So there are various methods of determining the solution of congruence modulo prime power, this congruence modulo m. So in this section, instead of m, we will denote it by p, where p here stands for a prime number and n stands for the natural number. We are going to obtain the solution of the congruence fx congruent to 0 modulo p to power n plus 1 from the solution of fx congruent to 0 modulo p to power n. So note that first of all we know that if this fx congruent to 0 modulo p to power n plus 1 has a solution, if it has a solution, then every congruence fx congruent to 0 modulo p to the power k, where k here is greater than or equal to 1 but less than or equal to n, will also have a solution. And why it follows? The result follows from here only. If this has a solution, then every polynomial or every congruence fx congruent to 0 mod p to power k also will have a solution because of this. If a is congruent to b mod m, if a is congruent to b mod m and n divides m, then a will be congruent to b mod n. So here also, if fx is congruent to 0 mod p to power n plus 1 and k here is greater than or equal to 1 but less than or equal to 1, which means that p to power k always divide p to power n plus 1. So once this have a solution, it means that every polynomial of this form fx congruent to 0 mod p to power k also will have a solution. In particular, suppose the congruence 2 has a solution, x is congruent to x1, means these are the only solution of this fx congruent to 0 modulo prime p to the power n, and if y is a solution of fx congruent to 0 mod p to the power n plus 1, then y will also be a solution of this congruence fx congruent to 0 mod p to the power n. Therefore, there will exist t such that t is greater than or equal to 0 but less than or equal to p minus 1, where p here stands for a prime, and y is equal to xi plus t into p to the power n. That is, y will be congruent to xi modulo pn, because x1, x2, dash xm are the solution of fx congruent to 0 modulo pn, and if y is also a solution of this, with y being the solution of equation 1, then y also being a solution of equation 2, it means that y will be congruent to xi, where I here varies from 1 to m. So which implies that t here will be, okay, there is no. And the method here, the following theorem will tell us under what condition this t will exist and how many such t's are there, okay, to obtain the solution of this system of congruence fx congruent to 0 mod p to the power n. So let me state this theorem. The proof is not needed, but in the notes I'll just give you the proof. I'll not explain it. It will be much clear to you by solving the problems using the statement of this theorem. So here this theorem states that let f of x be a polynomial over the set of integers and of degree r greater than or equal to 1, and let p be a prime, and n here is a natural number, n greater than or equal to 1, and let y be any solution of f of x congruent to 0 mod p to the power n plus 1. Okay, then y will be equal to xi plus tp to the power n, where xi here is greater than or equal to 0 but less than or equal to n, and xi is a solution. So this is a statement of the theorem. Based on this, we are going to find out under what condition that t exists and how many such t will exist. So here let fx be a polynomial over a set of integers and of degree r greater than or equal to 1, and let p be a prime number with n greater than or equal to 1, n here being a natural number, and let y be any one solution of fx concurrent to 0 mod p to the power n plus 1, then y will be equal to xi plus t into p to the power n, where xi here is greater than or equal to 0 but less than or equal to p to the power n, and xi is a solution of fx concurrent to 0 mod p to the power n, such that t here is greater than or equal to 0 but less than or equal to p minus 1, and t satisfy with these are the conditions for the existence of t, and t satisfy the concurrence t into f prime. F prime here stands means the first derivatives of f at the point xi, where x1, x2 dash dash xm are the solution of fx concurrent to 0 mod p to the power n, and this must be concurrent to minus f of xi by fxi here is a polynomial over the set of integers by replacing x by xi being the solution of fx concurrent to 0 modulo p to the power n divided by p to the power n modulo p. Furthermore, if h is the number of solution of the above concurrence, means if h is the number of solution of the above these concurrence, then h will be equal to 1, means the number of solution will be 1 or unique if p does not divide the first derivatives of this f at the point xi, and there will be no solution if p divides the first derivatives of fx at the point xi, and moreover p to the power n plus 1 does not divide the polynomial fx at the point xi, and h will have p solution if p divides the first derivatives of f prime of xi, means if p divides f of xi and p to the power n plus 1 divides f of xi. Here f of xi here stands for if you are given polynomial fx belong to set and x1 x2 dash dash xm are a solution, in general we'll write xi is a solution. If xi is a solution of fx concurrent to 0 mod p to the power n, then we must then you replace this x, that is f of xi is concurrent to 0 mod p to the power n, then p to the power n, that means that the number of solution of this concurrence fx concurrent to 0 mod p to the power n will be equal to p if p divides the first derivatives of this fx at the point xi, and moreover this p to the power n plus 1 divides the polynomial fx at the point xi. I hope it is clear, because the proof is, I'll give you the proof in the notes, but I'm not going to explain it. I'll explain step by step while solving the problems how to find the solution of the concurrence of this form x cubed plus x squared plus 1 concurrent to 0 mod 3 square. These are the types of problem. Based on this theorem, we are going to find the solution, whether the solution exists or not. If it exists, we are going to use this theorem to find out the solution of this polynomial x cubed plus x squared plus 1 concurrent to 0 mod 3 square. So that one will be discussed in the next discussion. Okay.